the last section in this chapter is on improper integrals. So the question is, what happens if we want to use infinity as one of our limits of integration? Or what happens if I want to integrate across a discontinuity, like an asymptote or something like that, okay? So let's imagine first that we want to evaluate this integral. We'll use the fundamental theorem of calculus, your f of b minus f of a. So we want to integrate from 1 to b. Well, this is going to be when we use our u substitution. We don't need u substitution here. This is simply going to be the integral from 1 to b of x to the negative 2 dx. So that comes out to, we add 1 to the exponent, x to the negative 1, divide by the new exponent, and we want to evaluate that from 1 to b. So we'll come up with negative 1 over b minus negative 1. So this simply comes out to negative 1 over b plus 1. If you can do that, you're halfway there. Okay, now let's think about this. For what values of b would that integral converge? Meaning, what values of b would give you an answer? Well, 0 would not, but anything on either side of 0 is going to give us a number that would converge. This is really the question, and since b has to be greater than a, we want really anything. It has to be greater than 1. So this would be for all x's. This would converge for all x's greater than or equal to 1. That's all we want for our integral. So this idea of whether the integral converges or not is the big idea here when we look at improper integrals. Okay, so there's several different cases where we would need an improper integral with an infinite integration limit. So what we must use, because we cannot do computations with infinity. You have to resist the urge to plug infinity into an equation. We cannot do that. So instead, infinity is a value we can approach. So we have to treat it like a limit. If I want to find the integral from a to infinity of f of x dx, then what we're going to do is we're going to choose some other variable to be where the infinity was. Typically we use b or a, depends on the situation. We've already got an a here, so we'll use b. What we want is the limit as b approaches infinity of the integral from a to b of f of x. And so again, this was where the infinity was. We're going to keep going and going as we approach infinity and see what happens. Now, if the infinity is on the bottom, then we're going to change and approach negative infinity on the bottom. And I do believe that this is a typo. We want our a to approach negative infinity. Now, if we have infinities on both the top and the bottom, that's okay, but we are going to have to split that integral. And you can pick literally any constant that's between negative infinity to positive infinity, so c can be any real number. So here's the idea. For both case 1 and case 2, if the integral converges, that means the limit is going to exist. So if that limit exists and you get a value, then we can say the integral converges to whatever that value is going to be. Otherwise, we say the integral diverges. If we think of this in terms of area, if the integral converges, that means that we can count the area under the curve. Even though it might be an infinite bound, we still could end up with a finite amount of area, which is kind of interesting. Otherwise, if we say it diverges, that means there's infinite area under the curve as well. For case 3, since you've got two separate integrals, you have to get two integrals that converge. Otherwise, if one of them diverges, then the whole integral is going to diverge, okay? Now, the most important thing here is you must use limit notation. On the AP exam, if you do not use limits, if you simply evaluate by plugging in infinity, you will earn exactly 0 of the points possible. So we cannot let that happen. So for example 1, we want to integrate from 0 to infinity of 1 over x squared plus 1 dx. So the first thing that we need to do is rewrite this using limit notation. The infinity is the problem. So we're going to take this now from 0 to b, and that means that we want the limit as b approaches infinity from 0 to b of 1 over x squared plus 1 dx. Hopefully you've seen it enough times now that you recognize that that's the arctangent. So we have not done our limit yet. We're still working on the integral. So we want the limit as b approaches infinity of, this is going to be arctangent of x, and we want that from 0 to b. So that means that we want our limit as b approaches infinity of, now we're going to apply the fundamental theorem, arctangent of b minus arctangent of 0. And now we're ready to evaluate this limit. So arctangent as b approaches infinity, it might be helpful to envision what the graph of arctangent looks like. When we have the graph of arctangent, remember it's a reflection of the graph of tangent over the line y equals x. There is a horizontal asymptote at pi halves and a horizontal asymptote at negative pi halves, and the graph looks like this, okay? So as we approach infinity, and this is honestly one that I would just put on a flashcard because it comes up so often. The limit as b approaches infinity of the arctangent of b is going to be pi halves, okay? That one comes up a lot, so you might as well just memorize it. Minus the arctangent of 0, which is 0, so the answer is pi halves. So we can say that the integral converges to pi halves, okay? So even though we're finding the area from the curve from 0 to infinity, it gets so teeny tiny at the end that we end up having a finite amount of area, which is kind of interesting, okay? So that's the answer to number 1. Let's go ahead and look at number 2. We want to evaluate, again, from 0 to infinity of x to the first. I don't really know why that 1 is there. We don't need it. Of x times e to the negative x dx. Okay. So we're going to first rewrite this using our limit notation. Very similar to the last one. Infinity's on the top, so we want the limit as b approaches infinity from 0 to b of x e to the negative x dx. Okay, in this case, if we want to evaluate this limit, or I'm sorry, this integral, it looks like we're going to have to use integration by parts. So what I would use for integration by parts is I'm going to choose u to be x because that gets simpler when I take the derivative. And I'm going to choose dv to be e to the negative x dx because that's easy to integrate. I get negative e to the negative x. Okay, so we want now the limit as b approaches infinity of, we've now got u times v, so that's going to be negative x e to the negative x, and this is a definite integral, so we still need it to go from 0 to b, minus the integral of v du. Well, this integral has a negative, so we can pull that out. So this is still from 0 to b of e to the negative x dx. And so we can see now that once we've got all of our integrals done, we get the limit as b approaches infinity of negative x e to the negative x. I'm just going to wait to evaluate these all at one time. Plus, this is, and I guess technically we can call that minus because we've already done this integral before. We're going to get negative e to the negative x, again from 0 to b. So now let's use FTC and expand those integrals there. So we have the limit as b approaches 0 of, this first one is going to be negative b e to the negative b minus, it's going to be 0. Okay, then we have minus, don't forget we're subtracting this whole result, so we get e to the negative b minus e to the 0, which is going to be 1. Now, I would adjust our negative exponents here because since we're doing a limit to infinity, it's helpful to see when we have a numerator and a denominator happening. So this is going to be negative b over e to the b, that 0 doesn't matter, minus 1 over e to the b plus 1. Okay, limits at infinity. If I have e to the infinity power, that's going to grow faster than negative b. So this one is going to go to 0. This one is also going to go to 0. And then we have plus 1. So this limit comes out to equal 1, which means that we can say that this integral converges to 1. Cool. All right. Now, the last thing that we want to look at is what if there is some sort of discontinuity in the interval? So for example, whoops, I almost stopped the recording. If we look at this next one, we want the integral from -1 to +1 of 1 over x dx. Well, that has an asymptote at x equals 0, right? So the question is, do we think this integral converges or diverges? Well, if you think about what this graph is going to look like, you can maybe make some predictions. Whoops, I'm scribbling. My pen's going crazy. All right. If you think about the graph of 1 over x, it looks like this, okay? So the area under the curve on one side is positive, on one side it's negative. It looks like they're going to cancel each other out and that the integral might converge. Or you might look at it and think there's infinite area on the right, infinite area on the left. Maybe this is going to diverge. We don't know. So the way that we would handle this is very similar to what we've done before. We still have to make a limit because we can't actually get to the asymptote, okay? So we're going to split this limit apart. Now what we have to remember is that from one side, we're going to be approaching 0 from the left, and on the other integral, we're going to be approaching 0 from the right. Remember that if any part of the integral and the limit diverges, or it doesn't exist, then the entire integral is going to diverge, okay? So here's how we would set this up. We know that the issue is going to be at 0. So I'm going to say the limit as b approaches, if I go from -1 up to 0, I'm going to be approaching 0 from the left. So this will be from -1 to b of 1 over x dx plus this one, the 0 is going to be on the bottom, so I'm going to call that one a, and we're going to approach this time from the right of the asymptote of the integral from a to 1 of 1 over x dx. Okay, so if we integrate this, we get the limit as b approaches 0 from, from the left. Okay, these integrals are all pretty easy to do. We're going to get the natural log in both cases. So here it is. We get the natural log of the absolute value of x in both cases. Now we need to apply that fundamental theorem, and so we get this. And now we need to think about this. Well, the natural log of 1 in both of these cases is going to be 0. That is, again, something that you want to have memorized, that the natural log of 1 is 0. So now we need the limit as b approaches 0 from the left of the natural log of b. Now if you think about the graph of natural log, it looks something kind of like this. And if we take the absolute value, that allows us to do the negative side as well, but it's going to look like this. So we can see from the left and from the right with natural log, the limit is going to be -infinity. So since the limit as b approaches 0 from the left of natural log of b does not exist, this integral is going to diverge. Also, the natural log of a is going to diverge, but it doesn't matter because it only has to mess up one time in order for it not to work. So the original integral has to diverge since those don't go together, okay? All right, example 4 is very similar to this one. Instead of having to split it, we just need to approach the 0 from the correct side. This will only have one integral. And then beyond that is just some practice from the AP exam. So I'm going to leave those last examples for you to look up in your notes. And be sure to check in with me if you have any questions. I'll see you soon.